Hello, everyone. My name is Sung-Hun Nam from Naver Webtoon 8i. I'm delighted to introduce our work titled Nearly Zero Cost Protection Against Mimicry by Personalized Diffusion Models. Through this presentation, I hope our proposed work can contribute significantly to protecting the creative ecosystem. Diffusion models are generative AI systems that produce images by progressively removing noise from random data, resulting in high-quality visual outputs. Let's briefly look at how unauthorized fine-tuning can misuse generative models, like Stable Diffusion. As illustrated in this diagram, a small number of unauthorized samples here images of a character named Yumi can be used alongside text prompts to fine-tune a diffusion model. Once fine-tuned, this modified model can effortlessly generate new content, replicating the original style or character. Such misuse raises significant concerns about copyright infringement and unauthorized content creation. Therefore, understanding and addressing these vulnerabilities is crucial. To address the issues previously mentioned, various perturbation-based protection methods have been proposed. These techniques prevent generative AI models from copying the content and artistic styles of original works. As shown in the diagram below, subtle adversarial perturbations, which are nearly invisible to human eyes, are embedded into the original images. This effectively hinders unauthorized imitation by generative AI models, as illustrated on the right side of the diagram. Previous perturbation-based protection methods mainly focus on balancing protection efficacy and invisibility, which significantly limits their practical usability. Typically, these approaches optimize perturbations during inference, causing substantial delays. For instance, PhotoGuard requires approximately 5 minutes to protect a 512-sized image on a CPU, and about 7 seconds on an A100 GPU, making real-time application challenging. To address these limitations, our proposed work specifically prioritizes practical use, aiming to ensure minimal latency during inference. Let me first provide some background. Most existing methods employ an iterative optimization process during inference, where protective perturbations are optimized individually for each given image. As shown in the diagram, these approaches iteratively adjust perturbations over multiple steps, in this example, by minimizing the distance between the latent codes obtained via a VAE encoder from the input image and the target image. Due to this multi-step optimization, calculating adversarial perturbations requires considerable latency, severely limiting practical applications. Therefore, there's a clear need for perturbation generation techniques that achieve significantly lower latency. To address latency issues associated with iterative optimization, we can consider adopting universal adversarial perturbation, initially introduced in the adversarial attack domain. UAP pre-computes adversarial perturbations in advance and directly applies these learned perturbations during inference. While this approach significantly improves inference speed, it typically yields lower protection efficacy compared to iterative methods. This is due to its limited perturbation capacity, as it applies identical perturbations regardless of the input image. Therefore, enhancing perturbation capacity remains an important area for further improvement. Considering the latency issues and perturbation capacity mentioned in the background, we propose Fast Protect. When designing Fast Protect, we addressed the issue of limited perturbation capacity by introducing multiple protective perturbations. Our method classifies latent codes obtained via a VAE encoder into distinct groups using k-means clustering and subsequently trains multiple perturbations. By employing multiple perturbations, Fast Protect significantly enhances protection capacity and allows adaptive selection of perturbations best suited for each input image. During our experiments, we observed that protection performance varies according to the composition of target images. We conducted tests using target images with 3 different complexity levels, as shown on the left. As illustrated in the results on the right, the degree to which a target image's characteristics appear in generated content differs significantly, depending on whether the target has simple or complex textures. Consequently, in Fast Protect, we adopted an adaptive targeted protection strategy that dynamically selects perturbations corresponding to the target image optimized for each input at inference. During our experiments, we observed that protection performance varies according to the composition of target images. We conducted tests using target images with 3 different complexity levels, and found that the degree to which a target image's characteristics appear in generated content varies significantly, depending on the simplicity or complexity of its textures. Consequently, in Fast Protect, we adopted an adaptive targeted protection strategy. Specifically, this strategy involves training separate multiple protective perturbations for each target image. Lastly, Fast Protect introduces an adaptive protection strength approach to further enhance invisibility. Specifically, at inference, Fast Protect first generates a temporary protected image, then calculates a spatial perceptual map between the input and protected images, using LPIPS. By applying this perceptual map to adversarial perturbations, Fast Protect adaptively adjusts perturbation strength according to human perceptibility. This allows us to effectively modulate the intensity of perturbations, ensuring stronger protection in less noticeable regions. From this slide onward, I'll share our experimental results, starting with inference latency performance. For a 512-sized image, Fast Protect achieves an inference speed of 2.9 seconds on a CPU and 0.04 seconds on a GPU, representing a substantial improvement, as highlighted in the graph. This remarkable speed-up is possible because Fast Protect does not iteratively optimize adversarial perturbations during inference, unlike existing methods. Instead, it pre-trains multiple perturbations in advance and simply applies the appropriate perturbation during inference. Next, we present the quantitative evaluation results. The left column shows the inference speed for each method, while the right column illustrates invisibility and protection performance across for different domains. These quantitative evaluations confirm that Fast Protect achieves significantly faster inference speeds, while also maintaining comparable invisibility and effective protection performance compared to existing methods. Additionally, Fast Protect demonstrated acceptable robustness against noise, JPEG compression, and image resizing compared to baselines. Finally, I'd like to share our qualitative evaluation results. We observed that image quality degradation due to protective perturbations was minimal compared to other methods. Additionally, we confirmed that protected images effectively reflect the target image characteristics as intended. Finally, I'd like to conclude this presentation by summarizing our key contributions. We propose Fast Protect, a method that achieves real-time protection against diffusion models, specifically addressing the critical issue of latency for the first time in this task. Fast Protect integrates perturbation pre-training with adaptive inference schemes, effectively meeting all the requirements of a practical protection solution. We validated Fast Protect across diverse scenarios and demonstrated that, despite its enhanced speed and invisibility, it successfully maintains protection efficacy, robustness, and generalization capabilities. Thank you very much for your attention. For additional details regarding our proposed method, please visit our project page. If you have any questions, feel free to reach out via the provided contact email. Thank you.